Multiplexers may seem pretty complicated at first, but their basic behavior at their core is really simple. So let's just draw a 2-input multiplexer and see how this works. So a multiplexer uses this kind of trapezoidal shape, and we'll adjust the shape to have as much space for inputs and outputs as we need. And so the multiplexer has 2 inputs. We'll call them D0 and D1 for data. And then it has a single select input for a 2-input multiplexer. We'll just call this A. Okay, so now, when A is 0, then we're going to select D0. And when A is 1, we're going to select D1. So when A is 0, whatever D0 is going to appear on the output Y. And when A is 1, whatever D1 is going to appear on the output Y, and D0 is going to be ignored. So A just lets us select either D0 or D1 to be the output Y. And as D0, when one of the inputs is selected, so if we selected D0, as D0 changes, those changes will be reflected at the output, as long as it continues to be the one that's selected. Now we can take a 2-input multiplexer and scale it up. So right now we just have one select line that's choosing between 2 inputs. We could have 2 select lines. So let's draw a bigger multiplexer here. And we'll have 2 inputs, we'll call them A and B. And with 2 inputs, we can choose between 4 possible data values. So we'd have 0, 0, 0, 1, 1, 0, and 1, 1 to produce our output Y. And so we'll call these 4 values data 0 through data 3. Okay, now, so if both A and B are low, then we would select D0, and D0 would be reflected, whatever D0 is will get copied out to the output Y. And likewise, if I select different combinations of A and B, being high and low, we'll select different ones of these data inputs. And we can go even further, write a really big multiplexer, and give it 3 data inputs. So we'll have A, B, and C. And now we will have 8 possible inputs and still one output Y. So again, the possible inputs are 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And then we could label these, for example, D0 through D7. Okay, that's all nice, but what are multiplexers actually good for? So it's kind of nice that we can say we can pick one of these 2 inputs, or one of these 4 inputs, or one of these 8 inputs, and copy that to an output. But so what? What do we do with that? Okay, so there's 3 different reasons I want to give you that might be useful for. 3 different places we might use a multiplexer or need one. So the first is that there are cases where you maybe need to be able to read a whole bunch of different values, but you only have a few wires. So imagine, for example, that we have a whole bunch of potential input values that we want to be able to read. So maybe we've got a microcontroller or some other thing, and we don't have enough pins. There's like too many things to read here, and we don't have that many pins on our microcontroller or whatever digital system that we're building on the other side. But as long as we don't have to read all of these pins simultaneously, as long as we can just check them one at a time, we can then connect a multiplexer and now these 4 inputs here have been multiplexed onto a single output here. And now we'll need a couple extra pins. We'll need something to control the select line, so some A and B. And so on a microcontroller, maybe this means that instead of having 4 input pins to read those, we now have 1 input pin and 2 output pins. So we've gone from 4 to 3, which is maybe not a huge win. But if I was to extend this out and I have an 8 input multiplexer, I only need 1 additional input pin, 1 additional select pin to get those extra 4 lines that I could read. So with 4 lines, I could read up to 8 inputs. If I was willing to go up to 5 lines, I could read up to 16 inputs. So the first reason you might use a multiplexer is it allows you to, with a small number of pins or a small amount of logic, whatever my magic reading stuff is over here on the right, can be reused for multiple inputs just by sticking a multiplexer in the input. But more importantly, a multiplexer is going to become our digital circuit equivalent of an if statement. So anytime you're writing some code, you might have something that says, if some condition, then do something in one case, so then this, else do that. Now in a circuit, we can implement this sort of the same basic if-else scheme by just using a multiplexer, and then this here is our result, and then we'll take our condition and use that to switch between the two. So depending on the state of condition, right, so this should be some kind of Boolean equation, just like in an if statement in computer code. And then we can put our 2 inputs here as the 2 possible values for the result. So we have this and that. And so depending on the condition, we can pick this or that, but not both, just one or the other, and then apply that to be the result. So for example, if we said like if A equals 97, and B equals 98, else B equals 66. Okay, so this is some simple thing we might write with computer code, and then we could just apply those values in a digital circuit to actually implement this basic logic function. So our condition just becomes, we have some box, some logic that is going to implement A equals to 97. That can go into our multiplexer, and then this is the value of B. And so if A is 97, so that would be the one case, we'll put 98 would be the value of B, and otherwise 66 is the value of B. Now, of course, a single wire can't carry the value 66, so we actually need a whole bus full of wires. So 66 would require 7 wires to represent that number in binary. And so we would actually need like a stack of 7 multiplexers here that are all switched by the same condition. But oftentimes we'll just draw it in this flat representation as if you could hold the number on just that wire. And just for simplicity and tidiness of the diagram. So the multiplexer lets us implement sort of basic if-else logic, and we're going to use this an awful lot, and you're going to see it coming up a lot once we start writing VHDL code. The third thing that multiplexers are good for is for implementing logic directly from truth tables. Not because it's actually a good idea to use multiplexers for this, but mostly because it's a logical bridge to the thing that we're going to be doing with FPGAs. And that is the subject of the next video.